Today we'll be solving this particular question on our screen. So the question says the entropy of a system can be expressed as a function of temperature and pressure of the system, and the total differential of S, which is the entropy with respect to pairs of variables, is defined as the S is equals to the partial differentiation of X, that's entropy, over the partial differential with time with respect to time at constant pressure dt, plus the partial differentiation of S with respect to P at constant temperature dP. They say assuming the system is ideal, starting from this expression, derive the equation change in S is equals to ncp ln ln T2 over T1 minus nr ln P2 over P1, where Cp, R, and N are the molar heat capacity, molar gas constant, and number of mole of the system respectively. Wow! So this is the question. So following this video step by step, though it might be kind of lengthy, but trust me, it's easy to understand if you follow this video one after the other, and make sure you are writing every step because it contains quite a lot of equations. So good. So let's start from the statement they said. They said entropy, that's S, is actually a function of temperature and pressure. Good. So with this, then we can actually conclude that the S is equal to the partial differentiation of S with respect to T at constant pressure dt plus the partial differentiation of S over dP at constant temperature dP. Very good. We can actually conclude this according to the particular equation they gave us today. Now, how do we now relate it to change in S is equals to ncp ln T2 over T1 minus nr ln P2 over P1? We need to find a particular equation that is actually relating all these terms that we have with this. Now, we should not forget that our H, which is enthalpy, is also a function of temperature and pressure. Very good. Our H is also this function. So we can also conclude that the H is also equal to the partial differentiation of H over dt at constant pressure dt plus the partial differentiation of H over the partial difference over with respect to pressure at constant temperature dP. Good. So we can also conclude this since our H, which is enthalpy, is also a function of temperature and pressure. Now, from first law of thermodynamics, we say our H is actually equal to U plus PV. Good. Our H is equal to U plus PV. And then if you say H is equal to U plus PV, then the H will be equal to du plus, you can say, P dV plus V dP, since you are introducing a change. Good. So we can actually conclude this. And then we should not forget that our U too, from that first law to our du, is actually equal to dq minus dw. Good. Now, from definition of enthalpy, we also conclude that okay, our dq is actually equal to T ds. That's what our dq is. If you can remember, from change in G is equals to, we have to change in H minus T change in S. So if you check this as Q, you can actually conclude that the Q is actually equal to T change in S, where our change in G will be equals to 0. So if you remember that, we can actually use that to get this. Okay, let me rub off this, though we don't need it, so we can know where that particular equation comes from. That's why we need that. Okay, so we have this, and then we should also not forget that dw is actually equals to P dV. that is what the W is equals to. So if I substitute all this, we can say, okay, our du is actually equal to T ds minus P dv. Okay, since we are getting into so many equations, let's start naming them. Let's put them with numbers so we can start relating them. So let's see, this is our equation 1. Let's call this equation 2. Good. Okay, so let's say this, let's call this equation 3, and then call this, okay, instead of calling this equation 3, since what we actually needed is this, let's call this equation 4. Good. And then we need this 2, let's call this equation 5. Good. So now with what we just derived, now let's substitute equation, let's say substitute, let's substitute equation, okay, this 3, sorry, it should be 3 not 4. Good. Let's substitute equation 4 in equation 3. Okay, we want to substitute equation 4 in equation 3. What's equation 4? Equation 4 is dh is equals to du plus p dv plus v dp. Very good. That's what we got for equation 4. Now then, our equation for equation 3, our equation 4 is du is equals to t ds minus p dv. That's du is equals to t ds minus p dv. So I can substitute that inside. So if I substitute this here, I'm going to have, since I have du here and also du here, so I can say, okay, my dh is actually equal to t ds minus p dv plus p dv plus v dp. You agree with me? That because this is this, so we just substitute this in. So I have this, just substitute it in here. Okay, so then our dh now will be equal to, since this is this and this can actually cancel out this, so we have t ds plus v dp. Very good. So I have this, let's call this now equation 5. Nice. So I can substitute, this is dh, let's go back and look at where we can see dh again. This is also another dh. Nice. So I can relate equation 5 to equation 2, since I'm having dh here and I'm also having my dh here, so it will be easy for us to see. Let's bring it this way. Good. So this is dh and this is also dh, so I can relate both. So let's say we want to relate. Good. Nice. Let me make it a little bit wider so we can see what we are doing very well. So relate equation 2 to equation 5. Now equation 1, what's our equation 1? Equation 1 is, we said our dh is a function of both temperature and pressure. That means, okay, is actually partial differentiation of h with respect to t at constant pressure dt plus the, okay, good, okay, good, plus the partial differentiation of h over with respect to p at constant pressure dp. So this is what we conclude at. Now I can, okay, from equation 5, sorry, my equation 5 says dh is actually equal to t ds plus v dp. Very good. Now I can relate both. This is the h and this is the h. That means these two things are actually equal to themselves. So I can make them equal. So making them equal, if I make them equal, I'm going to have t ds plus v dp is equal to, we have the partial differentiation of h. Please, this is partial differentiation. It's very, very important. The tp dt, good, plus we have the partial differentiation of h over partial differentiation of p at constant, please, this should be at constant temperature. This will be at constant temperature dp. Very good. Okay, now let's move on. So this is it. Now we should not forget that. We should not forget where we are coming from. It's very, very important, because we are relating to where we are coming from. Where we are coming from, if we check out very well from equation 1, what do we have here? We have ds. So all these two, let's try to make ds the subject of the formula. Do we get? So let's make this subject of the formula. So how do we make the s subject of the formula? That means everything we have in here, the only thing we want to see at this level is ds. So let me bring this vdp to this other side first. If I bring vdp to the other side, I'm going to have t ds is equal to the partial differentiation of h over the partial differentiation of, with respect to t at constant pressure dt, plus the partial differentiation of h over with respect to p at constant temperature dp. This will actually change to minus v dp. Very good. Okay, at this instance now, I can say, okay, this is dp, this is dp. I can bring dp out. I will have t ds is equal to, we have partial differentiation of h with respect to t at constant pressure dt, plus the partial differentiation of h over the partial differentiation of p. Let me actually open one bracket here. At constant temperature, we have dp here. Good. Now minus, oh please, before this, so writing dp again here. Good. Okay, now we have minus, since I'm bringing the p out, there will not be the p here again. I'm bringing this dp out, so we have v, and then I will have dp outside here. Very good. This will be very, very okay. So what did I do here? I just brought out this dp, since dp is common, right? Now we say we want to make ds subject of the formula. That means I have to divide all through by t, because I want to make ds subject of the formula. So if I divide all through by t, I'm going to have ds is equals to, we have over t. This is 1 over t, and yet we have also have 1 over what? T here, because I'm dividing all through by t. So t cancel out t, I will have ds alone here. So I have 1 over t. We have partial differentiation of ho with respect to t at constant pressure dt, plus we have 1 over t, open your bracket, we have the partial differentiation of h over dp, good, at constant temperature, minus v. Then we have what? Good, we have dp. Good, we have dp outside. So this is what we have here. So since I'm having this now, good, I have ds here, which I've successfully find here. Now for my equation, let's now call this, where did we stop? Let's stop. We stop at equation 5, right? We stop at equation 5. So let's call this equation 6. Good, we can call this equation 6. So equation 6 is ds is equals to 1 over t partial differentiation of h over t dt, plus 1 over t partial differentiation of h dp minus v dp. We have gotten that. Now equation 1, what does equation 1 state? Let's go back to equation 1. Equation 1 says the s is equals to what we can see here, right? So since I'm having the s ds there, I can relate both. So let's say, okay, we want to relate both now. Let's say relating equation 6 to equation 1. Very good. So let's relate both. So equation 1 says our ds is equals to the function of temperature and pressure. That means partial differentiation of partial differentiation of s. Good. So partial differentiation of s with respect to temperature at constant pressure, plus partial differentiation of s over with respect to p at constant temperature. Don't forget there is dt here, and we have dp here. Very good. So this is what we have at equation 1. If we bring this down very well, so we can see that this is what we have here. Good. So we have this here, and that's what we have written here, so we can see very well. Good. Okay, so we have gotten this. So let's now continue. So this is equation 1. This is what we derive from equation 1. Good. Now equation 6 is our ds is actually equal to 1 over t. We have dh over dt, constant pressure dt, right? Good. Plus 1 over t, open your bracket, we have dh over dp t minus v, and we have what? dp. Very good. So this is what we have gotten. Now from this we can start relating some things together. What are the things we can relate? Since we can see the ds here, that means they belong to the same family, and dp here, that means they also belongs to the same family. So because, and this is equals to, so this particular equation 1 is equals to this particular equation 6. I can relate both together. So by relating both together, I can conclude that, or we can conclude together that the s over dt at, sorry, good, the s over dt at constant pressure dt is equal to 1 over t, open bracket, we have del h over del t at constant pressure to dt. I can relate both together. Why can I relate both together? Because they belong to the same family. They have dt at the end of each of them. Do you understand? So dt can cancel out dt. Once dt cancel out dt, then I can actually have del s over del t p is equals to 1 over t. We have del h over del t at constant what? Pressure. Now if you have watched one of the video I dropped before this, we would know that the h over dt at constant pressure is equal to Cp, which is molar heat capacity at constant pressure. Do you understand? So dH over dt is equals to what? Is equals to Cp. Then I can actually conclude, since this is equals to Cp, then my del S over del T at constant pressure is actually equal to 1 over T to multiply Cp. And then we are going to have del S over del T at constant pressure to be equals to Cp over what? Over T. If we have just 1 mole, if you're having more than 1 mole, it will be equal to ncp over what? Over T. Are we good? So we can conclude that we have this as the s over the tp is equals to ncp over what? Over T. We have gotten that equation. Good. Now let's move on. We have gotten, let's call this equation, I think we stop at 6. This should be our equation 7. So let's say this is equation 7. Good. Now let's now move to how we can, if you are following up, you see we are getting to where we are going. Though I said it is lengthy though, so you actually find out that we are almost getting there. This is the equation we are looking for. I think we have gotten ncp, at least we have gotten ncp over t. So let's go, let's move on. So where we stop at now, we are almost there. Just for us to continue relating equation 6 to equation 1. We are not bringing out new equation again that much. So good. So let's relate equation 1 and equation 6 together again. So relating both together, yes, we said we have ds del s over del t at constant pressure to be equal to 1 over, good, we have 1 over t, good, sorry, you know why it's hanging, 1 over t. We have del h over also del t at constant pressure. We have cancelled out dt, so because this is having dt and this is also having dt, let's put it back, dt and dt. So okay, relate this is one. From that equation 6 and 7 to, good, from equation 1 and 6 to, we also says, since this is dp and this is also dp, looking for how we not even start going up and down again. Let me just bring out everything I need. ds over dt, good, at constant temperature. No, this should be okay. Wait, good. This is at constant temperature, so this should not be dt, this should be dp. Good, at constant temperature dt. This from equation 1, so is equal to the other one, which is equals to 1 over t, open bracket, we have del s over del p at constant temperature. Good, remove of this. Good, minus v, this is at constant temperature, minus v, and then we have what, dt out, if I'm not mistaken, yeah, from our equation 1. Okay, this should be not, no, I made that mistake. This should be dp because we have del p here, del p, so this should be dp. And book cannot be dt and dp. So let's move on. Good. So I mean, what I said there was this cannot be dt and this will also be dt. No, we're having two different variables there. So I want to be relating these two equations as we move on one after the other. So we'll be working out with these two equations one by one. Okay, now what do we do from here? dt, cancel dt out first, we don't need that. We have del s over del t, p is equals to, we have 1 over t del h over del t at constant pressure. Good. So I want to make del h over del t the subject of the formula. If I make del h over del t subject of the formula here, that means I need to call cross multiply, so this t will come here. So we have del h over del t at constant pressure to be equal to, we have del s over del t, we have t here since it's coming out, t at constant what, at constant pressure. So that's what I'm going to be having here. Good. Okay, since I'm having that, now let's differentiate with respect to pressure at constant temperature. Differentiate, we are differentiate with respect to pressure at constant temperature. Very good. So we are differentiating this with respect to p at constant temperature. So let's differentiate. If you differentiate this first one with respect to p at constant temperature, I'm going to have del square h over del t del p, good, to be equal to, since temperature is constant, it should just be there, and then I will have del square s over del t del p. Good. Let's call this equation 8. Okay, all this. Now let's move on to the next part. Here too we have dp will cancel out dp. So now we want to differentiate. Let's differentiate. Now it's not with respect to p any longer, it will be with respect to temperature. So differentiate with respect to we're differentiating with respect to temperature at constant pressure. So now we are differentiating with respect to what? To temperature. Now what is constant here is what? Is pressure. So then if I differentiate, please, before I differentiate, let me make my dh over dp the subject of the formula. Good. Okay, I think there is a mistake here. Yes, when we are relating equation 1 to equation 6. Good. My equation 6, this is 1 over, this should be the h. Good. This should be the h over the p from equation 6. Yes, this should be the h over the p t minus v. So this is the h, not the s. Okay, good. So with that, now if I make the h subject of, let me make the h subject of the formula here. That means I want to make this subject of the formula. Then I'll first also multiply to bring the t here. So we have del h over del t at constant temperature minus v is equals to t del s over what? Over del p. So I'll bring v. If I bring v to this other side, like bringing v here, I'm going to have del h over del t to be equal to t del s over del p plus v. So this is what I'm going to be having here. Good. Okay, so since I'm having this here, now let's continue. Now we said we want to differentiate with respect to what? With respect to we are differentiating with respect to temperature. Please, why do I keep on making this? This is dp. I don't know why I changed it to t. It is dp. Good. Don't forget this is at constant temperature before. Yeah. Good. So this is at constant temperature. Good. Sorry. Yeah. Good. At constant temperature, and this is constant temperature at constant temperature. So let's differentiate. So to differentiate this, I want to differentiate with respect to temperature. This is d, not 2. Yeah. So to differentiate with respect to temperature when pressure is constant. When pressure is constant. Let me write this variable so we won't be making that mistake. So we are differentiating with respect to temperature. This dp or del p, please. Del p. Very good. So differentiating this with respect to temperature, I'm going to have del square h over del t del p. Good. To be equal to we have t. Now temperature is not constant here. What is actually constant here now is pressure. We are differentiating with respect to t and p. So now we're having t here. Since we're having t here, t is not constant. That means we're going to be differentiating t2. But since we're having the product of two functions, we are going to be using product rule. So product rule means I'll first differentiate this when t will first stay as a constant first. Then we have t, we have del square s over del t del p. Good. Plus now we now need to differentiate t. If I differentiate t, then I'm going to have del s over del t del p. Very good. Okay, sorry. Good. I'm going to have del s over what? Over del p. Why? Because I've differentiated temperature. Good. Plus, then I'm having a volume here. So if I differentiate volume here, I'm going to have del v over del t. Don't forget, this is at constant pressure. Okay, so let's see what we come up with. Let's call this equation 9. Good. Let's call this equation 9. So we have been able to get this. So look at equation 8 and look at equation 9. There are some things that are common there. We have del square h dt dp. We have del square h dt dp. That means we can actually relate equation 8 to equation 9. So let's relate both together. So relating both together means we have t d squares over dt dp. Good. Is equals to, we also have t d square s over dt dp. Write this x very well. Good. Plus we have ds over dp. Plus we also have del v over del t at constant pressure. Okay, these things are the same. That means they are going to, if I bring it here, let me show us how we actually move with this. So if I bring this here, good, we're almost here. So we have, don't forget, this is t. If I have t, we have ds, this square s over dt del t del p minus t del square s over del t del p. We're going to be having is equals to del s over del p plus del V over del T at constant pressure. So this can cancel out the 0. So if I bring the V over the T to the other side, then I can actually conclude that del S over del P is actually equal to del V over del T at constant pressure. So I've gotten this. Now let's now go back to, let's call this, we can actually call this equation 10, I think. Yes. So let's call this equation 10. This is equation 9, so we can call this equation 10. Good. So like I said, we should not forget where we are coming from. Should not forget where we are coming from. So we are coming from equation 1. So let's see equation 1. What does equation 1 says? Equation 1 says ds is equal to the function of both temperature and pressure. That means del S over del T at constant pressure dt plus del S over del P at constant temperature is equals to del that's all. Okay, good. Dt, nice. So this is what we have for equation 1. So let's now start substituting one by one. So we can say ds is equals to, now going back to I think equation 6 or so. Equation 7. From equation 7, we denote that ds over dt is equals to what? ncp over t. That means, okay, let's see. Let me write it out. Let's write it out. Good. Okay, before we write this. Good. So from equation 7, we say del S over del T at constant pressure is equals to ncp over t. And from equation 10, good, let me rub this off. From equation 10, we got that ds over dp at constant temperature is equals to del V over del T at constant pressure. Very good. So let's try to relate both together. So we got this, and then equation 1 says this. So we can also say, okay, ds is equals to, instead of del S over dt, we can replace it with ncp over t, dt plus, instead of ds over dp, we can actually relate with we have, this is dp, please, not dt. Can relate it with dv del v over del t at constant pressure dp. Very good. Okay, so we have gotten both. So but we are close, but we are not still where we are actually aiming to. So let's see. For my gas law says nRT is equals to PV, or PV is equals to nRT. Now let's make V the subject of the formula. If I make V subject of the formula, I'm going to have nRT over P. Why am I doing this? Now we should not forget, see, I don't know why I keep on writing. This is the P. This is the P, please. This is the P. We are following this. This is the P and this is the P, please. So this is the P. Good. So let's get, so we are actually aiming this, we are actually going to this formula because if we want to integrate, we are going to integrate with respect to pressure, but there is no pressure here. So let's want to try to bring out pressure. That's why we bring in this particular equation, this ideal gas equation. So let's differentiate with differentiate V with respect to temperature partially, so that we making P the constant here. So we want to differentiate V with respect to temperature, making pressure a constant. So we are going to have del V over del T to be equals to n r over over P, because if I differentiate T here, it should just be 1. So, and don't forget I did this making P a constant. So instead of the V over the TP, we can replace it to n r over over P. So then we can actually say ds is equals to ncp over T dt plus, oh please, let's check out some things that I might have messed up. Good. So from this equation 10, when I brought in this one to this side, there should be a negative sign here. Good. There should be a negative sign here. So at the end of this, so when I'm bringing them in, so the s over dp is minus dv over dt. Good. So this is minus, there is a negative here, so this should be negative. Good. So this should be negative, there should be a negative sign here. Good. Very good. So there should be a negative sign here, so there should be negative, that's minus. So instead of our del v over dt, now we are going to be having nr over p dp. Good. So we are there already, but very close, very close. So let's now integrate. So integrate this, integrate everything. We want to integrate everything. ntp over t dt minus the integral of nr over p dp. So ncp are constant, nr are constant, so we can say, okay, if I differentiate this, I'm going to have change in s is equals to ncp will come out. Now 1 over t, if I differentiate 1 over t, it will give me ln, don't forget this will be t2 t1, yes, at two different temperatures. This should be p2 and p1. Very good. Nice. So this should be p2 and this should be what? p1. So we have ln, if I differentiate 1 over t, this is ln t. Ln t, we have t2 t1 minus, if I integrate p2 here, our nr2 are constant, nr will come out. So we have ln p, then we have what? p2 and what? p1. Very good. So since I'm having that, if I choose substitute t2 and t1 there, we have change in s to be equal to ncp ln t2 minus ln t1. Good. Minus nr, then I will have ln p2 minus ln p1. So we have changing s to be equal to ncp ln t2 minus ln t1 is actually equal to ln, open bracket, t2 over t1, t2 over t1, close the bracket, minus nr ln p2 over what? Over p1. So this is the equation that they asked us to derive. So that's it. So check it out. Check it out one by one. Let's go back. So you can see the steps one after the other. So follow those steps, very important. Okay, so let's expand this so we can get where we are going to. Good. So you can see what they are supposed to get. It said get change in S to be equals to NCP lane T2 over T1 minus N arrow lane P2 over P1, and that's what we actually got. So check it out, so that's it. So thank you so much for watching this video. So remember to like and subscribe. The major thing is try this on your own. We are going to be releasing one of the video just like this. In this video we did when changing S, that is, so entropy is a function of temperature and pressure. What about if it's the function of temperature and volume? What about that? So probably in the next video we are going to be talking about that, but for now let's digest this. Remember, this is gotten from Unilag past questions for thermodynamics student 300 level in Unilag. So check this out, it is going to be useful. Just make sure you get every step. Thank you so much. I remain a light. Till the next class, we see.